Is there another world in the near universe capable of supporting life? For a long time, researchers have pondered the possibility of other life on one of Earth's neighboring planets. Venus, Mars, Jupiter, Saturn, and even Uranus and Neptune, the ice planets. Today, researchers believe that life may have existed on Mars and may even subsist in pockets of water beneath the red planet's surface. The search for life on Mars dates back to the 19th century, and exploration missions are still underway. But more recently, scientists have turned their attention to the possibility of extraterrestrial life on celestial objects other than planets, the moons or satellites of planets. Today, technological advances are making the chances of discovering other life in the universe increasingly real. For a celestial object to harbor life, several factors must come together. First and foremost are the essential components of living organisms, known as organic compounds. These organic compounds are made up of carbon, oxygen, hydrogen, and nitrogen, simple elements that were already present in the cloud of gas and dust that gave rise to all the planets and their satellites. These elements could have been disseminated throughout the solar system billions of years ago by comets and asteroids. Then, for life to develop, there must also be water. Indeed, on our planet, it was water that enabled all these organic compounds to mix and interact, giving rise to primitive life forms. The third necessary ingredient for the appearance and development of life is a source of energy. On Earth, it's the sun that's essential for the chemical processes that give rise to life. For a long time, researchers thought that these three ingredients for life could only be found on a planet neither too close nor too far from the sun, like Earth. This is logical. If a planet is too close to the sun, it will be too hot, and if it is too far, it will be too cold. This zone, halfway between too close and too far away, is known as the habitable zone. In our solar system, only the Earth and Mars are located in the Sun's habitable zone. What complicates matters is that this habitable zone varies according to the nature of the star and the planet's atmosphere. Some stars shine brighter or dimmer than the Sun, and their habitable zones differ from those of our solar system. What's more, some planets may lie outside this habitable zone and still be capable of harboring life, as their atmosphere guarantees a reasonable temperature. The possibilities are numerous, even dizzying when you consider that researchers have identified 5,525 exoplanets to date, and the number is growing all the time. If the search for extraterrestrial life was already complicated, certain missions carried out on planets in our solar system have shaken all scientific certainties to the core. Many planets in our solar system have satellites called moons, and these moons are similar to planets, not only in size. Some moons are larger than the planet Mercury. Some have very active geological activity, like the Earth. For example, gigantic geysers have been observed on Triton, one of Neptune's 14 satellites. And some moons have gigantic underground oceans, with perhaps even more liquid water than on the entire surface of the Earth. There's no doubt that if planets like Mars could harbor life forms, then the moons of the planets in our solar system could also be potential candidates for the appearance and development of life. Dear traveler, welcome. Today we're off to discover the most impressive moons in our solar system. We're going to try to unravel their secrets and answer the question that's on researchers' minds these days. Will extraterrestrial life ever be found on one of our solar system's moons? But before you set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thanks, and have a great trip! Before we begin on our journey to the mysterious moons of our solar system, let's take a look at what we call moons. Moons are celestial objects that orbit a planet like satellites. There are over 200 known moons in our solar system. To date, NASA has counted exactly 214. The Earth has only one moon. With the exception of Mercury and Venus, all the planets in our solar system have several moons. Even dwarf planets like Pluto and many of the asteroids in our solar system have moons. Let's take a look at the planets in our solar system. Our neighbor Mars has two moons, Phobos and Deimos. These two moons are small bodies orbiting a few thousand kilometers from the red planet. Subject to the tidal forces of Mars, they rotate synchronously, meaning they always face the same direction as the planet. Their orbits evolve over time. Phobos moves closer to Mars, while Deimos moves further away. Let's continue moving through the solar system away from Earth. Neighboring Mars, the gas giant Jupiter is the planet with the most moons, with 92 confirmed satellites. Io, Europa, Ganymede, and Callisto, Jupiter's four largest satellites, are called Galilean satellites as they were discovered by Galileo in 1610. In fact, they were the first moons to be discovered after our own. Saturn is the second planet with the most moons, with 144 confirmed satellites, of which 66 have been given official numbers and 63 their own names. Saturn's two best-known moons are Enceladus and Titan, which we'll explore later in this trip. After Saturn comes the planet Uranus. 4 times larger than the Earth, it is the third largest planet in the solar system after Saturn. Along with Neptune, it is one of the 2 icy planets in our solar system. Uranus has 27 moons. The first 2 satellites of Uranus to be discovered, in 1787, Titania and Oberon, take their names from Shakespeare's play. Titania is the largest satellite of Uranus and the 8th largest in the solar system. Neptune has 14 confirmed satellites, the largest and first to be discovered in 1846 being Triton. Pluto, demoted to dwarf planet status in 2006, is part of a double system with Charon, one of its satellites. Pluto's 4 other satellites are Styx, Nix, Kerberos, and Hydra. Let's turn first to Jupiter, the largest planet in our solar system, but also the one with the most moons. Jupiter is the 5th planet in the solar system in order of distance from the Sun, from which it is 779 million kilometers, or 485 million miles on average. This gas giant is the largest planet in size and mass, ahead of its neighbor Saturn. Its average radius is 69,911 kilometers, or 43,500 miles, or 11 times that of the Earth, and its mass is 318 times that of our planet. In fact, Jupiter is so huge that it has been visible to the naked eye since prehistoric times. After the Sun, Moon, and Venus, Jupiter is the 4th brightest object in our night sky. In fact, its great luminosity is the origin of its name, which comes from the Roman god Jupiter, master of the other gods. Composed mainly of hydrogen and helium, Jupiter's composition is similar to that of the Sun. Although it has a rocky core of heavy elements, it has no solid surface. In its atmosphere, several elements have been detected, including methane, ammonia, sulfur and nitrogen compounds, and water ice. Jupiter, its 92 moons and rings, are known as the Jovian system. But the giant planet's influence extends far beyond the Jovian system. This influence is exerted, for example, on Jupiter's Trojan asteroids, a group of asteroids that share its orbit around the Sun. The first space probe to fly over Jupiter was the American Pioneer 10 in 1973. Until 1979, the planet was explored by Pioneer and Voyager 1 probes. Then between 1995 and 2003, the Galileo probe orbited Jupiter, followed by the Juno orbiter in 2016. Juno is currently still orbiting Jupiter, until at least 2025. Unfortunately, we've long known that the chances of Jupiter harboring life are remote. Not only does Jupiter have no solid surface, but its presence and internal temperatures are extreme. No biological object could survive on this type of planet. So why do Jupiter exploration programs continue to fuel the hopes of alien hunters? Because Jupiter has 92 moons, 4 of which could potentially be habitable. These are the famous Galilean moons. That Jupiter's moons are habitable is hardly surprising. The Jovian system is often compared to a miniature version of the solar system. Jupiter accumulated so much thermal energy due to gravitational contraction during its formation that it now releases more thermal energy than it receives from the Sun. It could therefore act for its moons like the Sun for the planets in our solar system. Jupiter's 4 Galilean moons were discovered by Galileo in 1610. The Italian astronomer gave his name to these satellites, although they may have been observed earlier by the Chinese astronomer Ganymede in 362 BC. Between the end of the 19th century and the early 1650s, 8 other satellites of Jupiter were discovered: Amalthea, Himalaya, Elara, Pasiphae, Sinope, Lysithea, Carme, and Anakie. Leda and Themisto were discovered in the 1970s. So, before the arrival of space probes on Jupiter, 14 satellites of the Jovian system were already known. In 1979, 3 more moons were discovered. The number of known satellites was increased to 63 by new observations at the turn of the century, and from 2010 onwards, new observations expanded the catalog of Jovian moons. The last 15 known satellites were discovered very recently, in 2022 and 2023. So it's possible that more will be found in the years to come. It's true that at first glance, Jupiter's moons don't seem very hospitable. They are far from the Sun, almost all encased in ice, and their atmosphere is very sparse. But their observation has revealed some fascinating facts that are well worth investigating. Galilean moons are likely to conceal liquid oceans beneath their icy crusts. And liquid water means the development of biological organisms. What's more, the thick ice crust could provide good protection against radiation and meteorites, as well as thermal insulation conducive to the development of life, a bit like our atmosphere on Earth. But let's take a closer look at these moons to find out more about their potential for harboring life. Fasten your seatbelts as we explore Jupiter's 4 Galilean moons: Io, Europa, Ganymede, and Callisto. Let's start with Io, perhaps the moon in the Jovian system least likely to harbor extraterrestrial life. You'll soon see why. Io is also called Jupiter 1, perhaps because it is the satellite of Jupiter whose orbit is closest to the gas giant. Its period of revolution is just 42 hours. It is Jupiter's 3rd largest moon and the 4th largest in the solar system. But it's also the densest and most geologically active, with over 400 active volcanoes. The fact that Io is so volcanically active first surprised scientists. When the Voyager probe flew over Io, it detected something unexpected on its surface: hundreds of giant active volcanoes. Other probes have since spotted huge lakes of molten lava. These discoveries are quite astonishing, as volcanic activity on Earth is fueled by the heat of the Earth's core. However, Io is so small that it must have cooled down completely billions of years ago. The only possible explanation was that Io certainly conceals in its core another source of energy that can continuously fuel this volcanic activity. The observation of volcanoes on Earth and the data collected on Io enabled us to imagine what life would be like on this moon. Living on Io would mean living in an extremely hostile environment, very cold or very hot, with no atmosphere. If you were to walk on Io, you would bounce slightly because the gravity on Io is the same as on the moon, 6 times less than on Earth. You could walk through black lava fields and witness phenomenal volcanic eruptions. Because on Io, eruptions are extremely spectacular. The gases released by the lava project clouds into the interstellar void. On its way to Pluto, NASA's New Horizons probe passed close to Jupiter in March 2007 and photographed an impressive volcanic eruption on Io. The eruption was that of the Tvashter volcano. The images taken at the time by the probe's high-resolution telescopic camera are impressive. They show a plume over 300 kilometers or 185 miles high, rising in Io's northern hemisphere and then raining down on the surface. These images provide researchers with proof that volcanic eruptions on Io are violent and powerful. But what could be generating so much energy in the heart of this frozen moon? In fact, this intense geological activity is the result of tidal heating. This heating is due to the friction generated inside the moon by its gravitational interactions with Jupiter and two other Galilean satellites, Europa and Ganymede, with which it is in orbital resonance. In other words, with each of its revolutions in its elliptical orbit around Jupiter, Io is buffeted by the gas giant's gravitational forces. When it reaches the point in its orbit closest to Jupiter, it undergoes a deformation of over 100 meters or 330 feet. Imagine this over billions of years, and you can see how intense friction could have arisen within this small moon. It's a bit like twisting and unfolding a piece of metal. It will eventually heat up. It's the same for Io. These movements and deformations have created an alternative energy source at the heart of Io, capable, in theory, of promoting life. Remember, life needs three elements to emerge, including a source of energy. With these discoveries, researchers realized that they had to stop believing that habitable celestial objects had to resemble the Earth in every way, and that habitable zones were necessarily dependent on the Sun. The perimeter, likely to harbor life, extended from the Earth to the farthest reaches of the solar system. However, the probability of life existing on Io remains very low. Yes, Io has an energy source. Yes, Io could contain the chemical elements that make up life, which would have been disseminated like on Earth by comets and asteroids billions of years ago. But researchers have never succeeded in finding the third element necessary for the emergence of life: liquid water or its equivalent. Why couldn't there be liquid water under Io's volcanic crust? Because, unlike other moons, Io is not made of water ice, but of silicate rock, surrounding a molten iron or pyrite core. Although the chances of Io harboring any form of life are slim to none, researchers are nonetheless interested in this moon for its intense volcanic activity. The interest of these volcanoes is not only scientific, but also aesthetic, as the images of this moon are magnificent. Io's volcanoes produce plumes of sulfur and sulfur dioxide, which, after rising several hundred meters, rain down and cover the moon's vast plains with a frosty layer of material. This material also forms a thin layer of atmosphere. Lava flows can extend over 500 kilometers or 310 miles in length. The moon's surface is constantly changing, taking on shades of yellow, red, green, white, and black. Io's surface is also dotted with over 100 mountains, the result of tectonic phenomena on the moon's silicate crust. Some of these mountains rise very high, even higher than Mount Everest, even though Io's radius is 3.5 times smaller than Earth's. Impressive, isn't it? There's no doubt that researchers won't be giving up their observations of this moon, which still conceals so many mysteries other than that of life. Let's continue our exploration of the Galilean moons with Europa, or Jupiter 2, the sixth closest moon to Jupiter. Europa has a period of revolution of 85 hours. With a diameter of 3,122 kilometers, or 1,900 miles, it's the smallest of the Galilean moons, but the sixth largest in our solar system. It's also the most interesting in the search for extraterrestrial life. In fact, according to researchers, it's the one where life is most likely to be found. Let's take a closer look at this mysterious moon. Europa has been flown over 12 times by NASA's unmanned spacecraft Galileo. Virtually all our data on Europa was collected by this probe. Europa is barely smaller than our moon. It consists mainly of silicate rock, with a crust of water ice and a core, probably of iron and nickel. It has a very thin atmosphere composed mainly of oxygen. Its temperature at the equator is minus 183 degrees Celsius, or minus 297 degrees Fahrenheit. And its temperature at the poles can drop to minus 223 degrees Celsius, or minus 370 degrees Fahrenheit. Unlike Io, or our moon, its surface is free of craters, making Europa the smoothest surface celestial object in the solar system. Its surface is relatively young, estimated to be just 100 million years old. Locked in by Jupiter's tides, Europa rotates synchronously around the gas giant, so it always presents the same face. Small deviations in its rotation have been observed. All these observations could mean that there is a liquid layer between the surprisingly smooth surface of this small moon and its rocky core. This hypothesis was confirmed by the Galileo probe studies of the satellite's interaction with Jupiter's magnetic field. While there are no impact craters on Europa's surface, there are glacial striations and fissures known as lineae. These crevices have been analyzed by the Galileo probe. The analyses show that in the past, the satellite's crust moved 80 degrees in relation to its interior, which would have been impossible without a liquid layer beneath the surface. What's more, as the Galileo probe got closer to Europa, it was able to observe these cracks more closely. The data collected suggests that in some places the ice cracked, then a trench formed, and a material filled the empty cracks and froze, allowing the parts to be welded back together. It's a bit like kintsugi. The probe also showed huge fields of jagged ice, as if the ice had melted and then roughly reconstituted itself, reminiscent of the ice that covers our oceans on Earth. The Galileo probe also took measurements of Europa's magnetic field. Analyses revealed the presence of an electric current that could correspond to that of a salty ocean of liquid water. According to the prevailing model, Europa's slightly eccentric orbit, maintained by its orbital resonance with Io and Ganymede, causes a tidal heating effect, allowing the ocean to remain liquid. This leads to a movement of ice, similar to plate tectonics, the first time this mechanism has been found anywhere other than on Earth. Like Io, Europa is therefore heated by internal friction due to its interaction with the gravitational fields of Jupiter and the satellites with which it is in orbital resonance. This may explain the jagged ice, which appears to have been melted and then refrozen. These interactions would cause powerful tidal waves in its inner ocean, further raising the temperatures inside the satellite. All this makes the presence of a liquid ocean possible. According to the researchers, this internal ocean could be as deep as 100 kilometers or 60 miles, with a volume twice that of our oceans on Earth, nicknamed the Blue Planet. Europa thus appears very different from its sister moon Io. It is covered by an exceptionally smooth and clean layer of ice. The highest features of its relief rise only a few hundred meters above the surface, a completely different landscape from Io's high mountains. The thickness of the ice crust varies between 10 and 30 kilometers or 20 miles. Europa's surface is striated by a network of long, deep fissures. Some of these cracks may be reaching the groundwater layer. If this is the case, the ice that covers the bottom of the crevices provides valuable material for studying Europa's interior composition. Europa's geysers occur regularly throughout the Moon's orbit, but are most frequent when the Moon is furthest from Jupiter. This is because Jupiter's tidal forces are weaker when the Moon is further away. These tidal forces are responsible for the formation of geysers, forcing water from the underground ocean towards the surface. These geysers, detected by the Hubble telescope, can reach up to 200 kilometers or 125 miles in height. These giant jets are made up of water vapor, a surprisingly clean form of water. It's possible that this water comes from Europa's underground ocean, or from giant lakes hidden beneath the ice crust. These are invaluable to scientists, as they would enable them to detect traces of life without having to use a lander. For the moment, nothing is certain. In the absence of concrete data, the composition of Europa's ice crust is currently estimated on the basis of one of its largest craters. Spectral analysis of the craters reveals compounds of magnesium, sulfur, iron, and hydrogen peroxide. Conclusion: there is certainly a wide diversity of minerals in the satellite's hidden hydrosphere. It's also important to point out that Europa's atmosphere contains oxygen, which is formed when icy water is broken down by UV rays. But Europa's gaseous envelope remains a trillion times sparser than that of the Earth. In any case, according to some calculations, the oxygen concentration in Europa's oceans could be sufficient to sustain single-cell aerobic life. Aerobicity is the ability of an organism or microorganism to thrive in ambient air using oxygen. Europa has liquid water and the building blocks of life. We still need a third element to affirm that life can develop there, a source of energy. And it does have a source of energy, undersea volcanoes that saturate the water with sulfur and iron oxides. Some researchers even claim that there could be multicellular organisms in the European Ocean, but this hypothesis is still premature. In any case, all we know is that we can't rule out the possibility of primitive life on this mysterious moon of Jupiter. Faced with all these possibilities, researchers are wondering whether it is really possible for a form of life to survive in this type of environment, namely, a cold liquid ocean enclosed beneath kilometers of ice, with no access to the sun's energy and with underwater volcanic activity as its sole source of power? The answer could lie on Earth. Biologist Tim Schenck has explored the waters of our planet that bear the closest resemblance to the icy depths of the Jovian satellite. 320 kilometers or 200 miles from the North Pole, the biologist sent robots 3,600 meters or 12,000 feet deep beneath the Arctic ice sheet, where sunlight never breaks through. In other words, the robots were sent into an ultra-hostile environment where temperature and pressure levels are extreme due to underwater volcanic activity. The aim? To understand what might be going on beneath Europa's ocean by observing the most hostile underwater environments on our planet. At depths of 3,600 meters or 12,000 feet in the heart of the Arctic Ocean, Tim Schenck's robots, unsurprisingly, collected evidence of a very hostile environment. Volcanic fissures spew water at 370 degrees Celsius or 698 degrees Fahrenheit, saturated with toxic chemical compounds such as hydrogen sulfide. This type of fissure is more than likely to be found in the depths of Europa's oceans. Surprising as it may seem, Tim Schenck has discovered living organisms around these cracks. These cracks are in fact lined with microbes for miles around, new forms of life that we never knew existed, but which are indeed living organisms. Even the polar oceans on Earth harbor microbial life, so why not on Europa? How do these microbes survive in such a hostile environment? Instead of using the sun's energy, they use sulfur, methane, and hydrogen as a source of chemical energy. The next step is to land a probe on Europa to verify the scientists' theories. But for that, we'll have to wait a little longer. For one thing, the Moon is 628 million kilometers away. What's more, we'd have to build a robot capable of crossing kilometers of ice, then swimming in the icy water to collect data. This is already a complex task on Earth, so imagine it over 600 million kilometers from our planet. Are moons that generate heat as they make their revolution, causing the ice to melt and underground oceans to form, ideal for the development of life? A far-fetched idea? Perhaps not, as Europa is not the only moon that could fit this model. Ganymede, or Jupiter 3, is the third Galilean satellite. Its orbit lasts about 7 Earth days. It is not only Jupiter's largest satellite, but also the largest in the entire solar system. In fact, it's the satellite that most closely resembles a planet. Its diameter is 5,268 kilometers or 3,000 miles, or 8% larger than the planet Mercury and 2% larger than Saturn's largest moon, Titan, which we'll study later. However, its mass is only 45% that of Mercury, as it is made up of equal amounts of water ice and silicate rocks, whereas Mercury is made up solely of rocks and metals. Ganymede is just over twice the size of our moon and twice as heavy as our satellite. You can see it with the naked eye in our night sky. It's the only satellite in our solar system with a liquid metal core and its own magnetosphere. This magnetosphere was probably created by convection within the liquid iron core. Ganymede completes its orbit around Jupiter in 7 Earth days, around 1 million kilometers from the gas giant. Its orbit is slightly eccentric and inclined to Jupiter's equatorial plane. Its rotation is controlled by Jupiter's gravitational tidal effects, like Io and Europa, so it too is in synchronous rotation. When Ganymede makes one complete revolution around Jupiter, Europa makes 2 and Io 4. Ganymede is therefore in orbital resonance with the other 2 Galilean moons. Ganymede's atmosphere is thin and contains several elements: atomic oxygen, dioxygen, and possibly ozone, as well as atomic hydrogen in small proportions. Pioneer 10 was the first probe to take a close look at Ganymede. In the 1970s, the American probes Pioneer 10, Pioneer 11, and Voyager 1 and 2 provided some insight into Ganymede. Then, the Galileo probe refined some of the data we have on this Jovian satellite, thanks to 6 close flybys between 1996 and 2000. Thanks to Galileo's data, we were able to discover its underground ocean and magnetic field. Like Europa, Ganymede is thought to have an ocean under its surface ice, which could contain more water than all the oceans on our planet put together. 1/3 of the satellite's surface is covered by 4-billion-year-old impact craters, and 2/3 by lighter-colored regions cut by wide grooves. This relief is probably the result of tectonic activity, triggered by tidal heating, although for the moment it remains a mystery to scientists. Some researchers believe that Ganymede has an ocean sandwiched between 2 layers of ice, while others think that there are several layers of ocean separated by different layers of ice, a bit like a mill fuel of water and ice. Ganymede's magnetic field is due to its iron-rich liquid core. As the magnetosphere is essential to protect us from radiation coming from space, the existence of this magnetic field is an argument in favor of the presence of life on this moon. Ganymede's magnetic field produces polar auroras, as shown by images taken by the Hubble telescope in 1995. Another feature of this magnetic field is that it is contained within the larger magnetic field of Jupiter. Studies of Ganymede's magnetic field by the Galileo probe show that there could be a multi-layered salty ocean beneath the ice crust at a depth of at least 200 kilometers or 125 miles. Multi-layered because this ocean could have up to 4 layers, each with its own salinity and density. These 4 layers would be separated by ice. On the surface of Ganymede, Galileo's high-resolution spectroscope has revealed the presence of a large number of non-aqueous materials. These include carbon dioxide, sulfur dioxide, sulfuric acid, various organic compounds, magnesium sulfate, and sodium sulfate. These materials probably originate from Ganymede's subglacial ocean, although it is not yet known by what mechanisms these compounds could have reached the surface by penetrating the satellite's crust. Researchers believe that Ganymede may have formed by accretion, i.e., the progressive agglomeration of the gases and dust that surrounded Jupiter after its formation. The average surface temperature of Ganymede is -148 degrees Celsius or -234 degrees Fahrenheit. A decay process inside Ganymede would heat the satellite even more, so that the core would have an average temperature of 1200 to 1400 degrees Celsius or 2550 degrees Fahrenheit. The presence of oxygen in Ganymede's atmosphere is not in itself proof of the presence of life on this satellite, as molecular oxygen can result from the decomposition of water ice under UV light. During this process, hydrogen evaporates into space, and oxygen, a heavier element, is deposited on the surface. For the moment, nothing is certain, but Ganymede remains a moon to keep a close eye on in the quest for extraterrestrial life in our solar system. We're now going to explore Jupiter's last Galilean moon, Callisto. Callisto, or Jupiter 4, is the second largest Jovian moon after Ganymede and the third largest in the solar system. It is the Galilean moon furthest from Jupiter, and therefore the only one of the four not to be in orbital resonance. Like Ganymede, Callisto is thought to have formed by accretion from the disk of gas that surrounded Jupiter after its formation. With a diameter of 4,820 kilometers or 3,100 miles, Callisto is roughly the size of Mercury. This moon has a thick crust of ice, 80 to 150 kilometers deep. It is made up of roughly equal parts rock and ice. However, it has one major difference from Ganymede. It does not undergo tidal heating and is therefore only partially differentiated. In other words, it does contain layers of different densities, but not at full depth. According to data collected by the Galileo probe, Callisto may have a small silicate core and an ocean of liquid water more than 100 kilometers beneath its surface. As on Ganymede and Europa, this ocean could harbor life. Its depth is estimated at between 50 and 300 kilometers, depending on the model, and its temperature would be around minus 20 degrees Celsius or minus 4 degrees Fahrenheit. Because of the high pressure, the water in this ocean would remain liquid. But beneath this ocean probably lies a layer of ice 300 kilometers or 185 miles thick, and a core composed of ice and rock. Callisto's surface is old, heavily cratered, and shows no sign of tectonic activity. Because Callisto is further from Jupiter than the other Galilean moons, its surface is less affected by the gas giant's magnetosphere. Callisto is surrounded by a thin atmosphere composed mainly of carbon dioxide and probably molecular oxygen, as well as by an intense ionosphere. Explored on numerous occasions by space probes such as Pioneer 10 and 11, Galileo, and Cassini-Huygens, Callisto is often considered the most suitable body for a human base to explore the Jovian system. However, the likelihood of this satellite harboring any form of life is lower than for Europa or Ganymede. The impact of Jupiter's tides is not enough to properly deform the satellite, as Callisto is located too far from Jupiter. As a result, the satellite cannot draw much heat from the gas giant. What's more, Callisto is made up mainly of ice, whereas it would be preferable for water to be in contact with hard rock to be saturated with the elements necessary for the appearance of life. In fact, the low diversity of chemical compounds and low temperatures on this satellite considerably reduce the chances of life appearing and developing. But this possibility should not yet be totally ruled out. Unfortunately, no more is currently known about the possibility of extraterrestrial life on Jupiter's moons. These moons have been explored only briefly, by spacecraft en route to another destination. But more recently, projects dedicated to the study of Jupiter and its moons have emerged. NASA's Juno probe arrived in Jupiter's orbit in July 2016 and has since delivered extraordinary images of the gas giant. In July 2021, it moved on to study the Galilean moons. On September 29, 2022, it flew very close over the moon Europa, passing just 352 kilometers, or 220 miles from its surface. This was only the third time a probe had flown over this satellite. The flyby enabled the probe to take photos of the moon, as well as samples, to be compared with Galileo data collected at the beginning of the century. On October 16, 2023, images of Io were revealed by the American probe, which passed within 11,645 kilometers, or 7,500 miles of the moon. The European Space Agency's JUICE project is also eagerly awaited. Its aim is to study Jupiter and the 3 Galilean moons that could harbor life: Ganymede, Europa, and Callisto. JUICE stands for Jupiter Icy Moons Explorer. The probe was launched on April 14, 2023, and is scheduled to arrive in orbit around Jupiter in 2031, after a 7.5-year journey. This positioning will enable it to fly repeatedly over the Galilean moons to collect data. Researchers have high hopes for this project, because if all goes well, it could considerably enrich our knowledge of Jupiter and its satellites. In December 2034, the probe will orbit Ganymede to study this satellite in greater depth, before completing its mission in September 2035. Another mission is being developed by NASA, this time to study the moon Europa in depth. This is Europa Clipper. This automatic probe should leave Earth in October 2024 and reach the Jovian system in April 2030. These projects are promising and should help us learn more about the presence or otherwise of highly resistant living organisms in the subterranean oceans of these moons. Researchers don't expect to find little green men on these satellites, but rather simple organisms like those found on Earth, at the bottom of the oceans near areas of volcanic activity. But it's a good start, since life on Earth probably evolved from these ultra-resistant microorganisms. Could there be other moons in our solar system with conditions similar to Europa, Ganymede, or Callisto, suitable for the appearance and development of life? The Cassini-Huygens space mission was designed to answer this question. Its objective? To explore the Saturnian system, i.e., the planet Saturn and its satellites, determine how Saturn's rings were formed, and inspect some of the giant planet's moons. This mission, developed by NASA with the participation of the European Space Agency and the Italian Space Agency, was launched on October 15, 1997, and ended on September 15, 2017. After flying past Jupiter on December 30, 2000, the probe was placed in orbit around Saturn on July 1, 2004. On January 14, 2005, the Huygens lander detached from the probe and landed on the surface of Titan, Saturn's largest moon, while the Cassini orbiter continued to collect data on Saturn and its satellites as they passed close to the gas giant's orbit. The mission was scheduled to last 4 years but was extended twice, ending on September 15, 2017. The Cassini orbiter was equipped with the most sophisticated instruments ever taken to the outer solar system: cameras, spectrometers. Particularly costly, this mission was a real success, as it provided scientists with a wealth of data on the Saturnian system: Saturn, its magnetosphere, its rings, Titan, and the other satellites of this giant planet. Thanks to the Cassini-Huygens space mission, Saturn's rings have been revealed in detail for the first time. These rings stretch for thousands of kilometers, yet in some places they are no thicker than a few dozen meters. The Cassini probe has confirmed that these rings are made up of billions of shiny particles of almost pure water ice. These particles vary enormously in size, from a speck of dust to a mountain. The data collected has also made it possible to date the rings. They were created less than 100 million years ago and should disappear in less than 100 million years. But above all, the Cassini-Huygens mission has also enabled us to refine our knowledge of Titan and to discover astonishing features of Saturn's other moons, notably Enceladus and its geysers, clues to an underground ocean that could perhaps harbor a form of life. In all, Saturn has 146 satellites, 144 of them confirmed. It also has more than 150 helices in its rings, which could be minor moons, i.e., particularly small natural satellites. At least 150 minor moons have been detected in Saturn's rings through the disturbances they create in their environment. But researchers suspect that this is only a small portion of the total population of these objects. Saturn's satellites vary in size, from less than a kilometer in diameter to 5,149 kilometers, or 3,200 miles in diameter, for its largest satellite, Titan, which is larger than the planet Mercury. We'll now take a look at Saturn's two most notable satellites, Titan and Enceladus. Let's begin our journey into the heart of the Saturnian system by exploring Titan, the largest of Saturn's moons. Titan, or Saturn VI, is the second largest moon in the solar system after Ganymede. It was the first moon of Saturn to be discovered by Dutch astronomer Christian Huygens in 1655. One of Titan's special features is that it is the only known satellite to have a dense atmosphere. Its atmosphere is made up of 98.4% dinitrogen and 1.6% methane and ethane, and lies between 200 and 880 kilometers in altitude, i.e., almost 500 miles above sea level. To give you a point of comparison, on Earth, 99.99% of the mass of the atmosphere is less than 100 kilometers or 60 miles above sea level. It's also difficult to obtain a spectrum of Titan's surface, as its atmosphere is opaque over a wide range of wavelengths. Titan's atmosphere contains layers of opaque fog that block out most of the sun's light, so much so that the Huygens probe team described the process of photographing Titan's surface as photographing an asphalt-covered parking lot at dusk. The temperature of the atmosphere is around minus 180 degrees Celsius, or minus 292 degrees Fahrenheit, and reaches minus 200 degrees Celsius, or minus 328 degrees Fahrenheit, at the tropopause, at an altitude of 40 kilometers, or 25 miles. According to observations by the Voyager probes, the pressure at the satellite's surface exceeds 1.5 times that of the Earth. Titan is composed mainly of rock and frozen water. Its surface is geologically young, with a few mountains and cryovolcanoes, but overall, a relatively flat and smooth surface, with few impact craters. Winds and methane rains, which are frequent on Titan, create dunes and coastlines on the satellite's surface, just like on Earth. Titan also has seasons. When Cassini's Huygens module visited Titan in 2004, it detected elements of life in its atmosphere. But that's not all. As it flew over the Moon, it detected something mysterious, partly hidden by the clouds gathering over its south pole, resembling a lake of water. Numerous flybys subsequently revealed the existence of hundreds of such lakes, scattered across the Moon's north and south poles. What is the significance of these mysterious lakes? Could it be that, as on Earth, they are lakes of water with a rich ecosystem? This question has intrigued researchers, as Titan is the only known environment other than Earth to feature liquid expanses on its surface. But given Titan's surface temperature of minus 180 degrees Celsius or minus 290 degrees Fahrenheit on average, these lakes cannot be lakes of liquid water. After analyzing the infrared waves reflected by the lakes, the researchers concluded that they were in fact liquid methane and ethane, at very low temperatures. On Earth, these elements are used as fuel in gaseous form. But on Titan, liquid methane digs valleys, forms clouds, and falls as rain. In fact, it behaves exactly like water on Earth. Researchers then wondered whether this methane could be conducive to the formation of life, allowing organic molecules to dissolve, mix, and interact, just like water on Earth. Our theory of life includes the need for a liquid element. On Earth, water enables organic molecules, the basic ingredients of life, to dissolve, assemble, and interact with each other to form larger, more complex molecules, destined to develop into living beings. But could another liquid do the trick? Could the building blocks of life dissolve in methane and give rise to life? Astrobiologist Chris McKay has attempted to answer this question. To do so, he used the elements detected in Titan's atmosphere by the Cassini mission and carried out a simulation. First, he reproduced the reaction that takes place on Titan to obtain the same organic material as in its atmosphere. Next, he recreated the lakes detected by the Huygens module's radars by filling a test tube with methane gas, which he cooled to minus 143 degrees Celsius or minus 225 degrees Fahrenheit using liquid nitrogen. The methane liquefied exactly as it does on Titan's icy surface. Chris McKay was thus able to obtain a miniature Titan lake in his test tube, namely, a bath of liquid methane with organic materials. The aim now is to find out whether these materials will dissolve to form more complex molecules and ultimately a new form of life. If these organic materials can dissolve, it means that the chemical processes necessary for life could exist on Titan, and on a larger scale, that they are capable of being triggered even in conditions of extreme cold and in liquids other than water. This would also mean that life has arisen twice under different conditions, and that it is therefore a natural process that can appear in other places. This would open up infinite possibilities. In any case, if there is life on Titan, it bears no resemblance to life on Earth. While we await the results of Chris McKay's experiment, other evidence of possible life on Saturn's satellite has been put forward. A team of researchers has identified a deficit of acetylene on Titan's surface. This molecule, which forms on the planet's surface, should be present in Titan's lakes, but has not yet been detected. According to Chris McKay, acetylene could indeed be the food of choice for hypothetical life based on liquid methane, but nothing is certain yet. The lack of acetylene could just as easily result from the action of sunlight or cosmic rays, which are capable of transforming acetylene into other, more complex molecules that no longer display its spectral signature. Whatever the case, researchers are still hopeful of finding some form of life on Titan. This moon of Saturn closely resembles a primitive Earth, albeit at a lower temperature in many respects. Its liquids on and below the surface, its thick atmosphere of diazote, Titan could well contain extraterrestrial microbial life, or at least a prebiotic natural environment rich in complex organic chemistry. Another of Saturn's moons has attracted the curiosity of researchers, Enceladus. On the face of it, this satellite isn't the most interesting. It's only Saturn's 6th in size and 14th in distance. But since the Voyager 2 and Cassini-Huygens missions, researchers have been taking a close interest in this small moon, which boasts some astonishing features. Enceladus is a real mystery, very different from Saturn's other moons in its appearance and shimmering white surface. It displays a complex geological activity, difficult to explain for such a small body. Indeed, Enceladus measures only 500 kilometers or 310 miles in diameter on average. However, the Cassini probe has spotted cracks, protrusions, and fissures on its surface, showing that there has indeed been activity on this moon. In fact, one of the objectives of the Cassini-Huygens mission was to find out whether this geological activity was still taking place today. Take a close look at these images taken by the Cassini probe. You can see 4 strange blue faults running parallel down towards the South Pole. These faults have been nicknamed the Tiger Stripes. 120 kilometers, or 75 miles long, they are several hundred meters deep and bear disturbing similarities to earthly faults. The probe's thermal sensors recorded some surprising data at Enceladus's South Pole. While these faults should be colder than the rest of the moon, they radiate heat. In fact, the faults are on average 95 degrees Celsius or 200 degrees Fahrenheit hotter than the rest of the moon. The mystery surrounding Enceladus thickened when the probe changed its perspective. As Enceladus passes in front of the Sun, immense geysers can be seen, erupting from the Tiger Stripes. These immense jets of matter rise up to hundreds of kilometers. So, does Enceladus harbor an energy source like Io or Europa that could explain these geysers? The answer is yes. Like the two Galilean moons, friction generated by gravitational forces causes the moon to heat up and melt ice. As it approaches Saturn, the moon Enceladus undergoes a torsion that creates internal heating, exactly what happens when a piece of metal is bent. The jets observed by the Cassini probe are in fact liquid water vaporized in space, freezing on contact with its icy temperature. These jets are propelled at an impressive speed of nearly 200 kilometers per hour or 125 miles per hour. So there could be liquid water beneath the surface of Enceladus. The Cassini-Huygens space mission team programmed the probe to pass through these jets in order to sample particles and better understand their origin. After several passes, the probe detected some of the elements that make up living organisms. The discovery confirmed that yes, there could be life on Enceladus. The moon contains 3 elements needed to be considered potentially habitable: liquid water, a powerful heat source, and organic material. What would life be like on Enceladus? Around the tiger stripes, we'd be in a region of eternal snow, since it's been snowing on Enceladus for at least 100 million years. The sky would be black, and we'd have the impression of floating due to the low gravity. We wouldn't be able to see anything with the sun at our backs, but facing the sun, we'd be able to see the immense geysers cut through the light and fall to the ground in a thick white mantle. For the moment, there is no evidence that Enceladus harbors life. Cassini's instruments have not detected any trace of life as such. But Enceladus is definitely on the list of next destinations to visit during space exploration missions. What's more, to analyze the moon's underground water content, you don't have to dig as you do on Europa. Just walk through the geysers. All the particles are sent into space, ready to be collected and analyzed. Apart from the Saturnian and Jovian systems, are there any other moons in our solar system that could potentially be habitable? Of the 214 moons identified by NASA, there must be more. To answer this question, scientists have turned to Uranus, Neptune, and Mars. Uranus and Neptune were overflown in the 1980s by the Voyager 2 probe. Scientists held out little hope of the habitability of these icy planets, which could not harbor liquid water, but after the discovery of oceans in unlikely places, the data collected on these planets and their satellites was revised. Uranus has 27 moons, but only 5 have been analyzed in depth: Titania, Oberon, Umbriel, Ariel, and Miranda. If an internal ocean existed on Miranda, the smallest of the satellites studied, it would probably have frozen over by now. But it's entirely possible that the other 4 moons contain an internal ocean. Depending on the moon, scientists have developed different scenarios to explain the origin of an energy source. On Titania and Oberon, the 2 largest satellites, heating is thought to be due to the tidal effect of Uranus, while on Ariel, it could be explained by cryovolcanic activity. The scientists' conclusion is that there may be internal oceans on the Uranian satellites, but they are relics of former oceans, or residual oceans, rather than thick oceans. And what about Neptune? The 8th planet from the Sun, Neptune, like Uranus, is what we call an icy planet. Of its 14 satellites, the one that most interests researchers is Triton, its largest, with a diameter of just over 2,700 kilometers, or 1,700 miles. Triton is an astonishing moon. It's the only known large satellite in the solar system to orbit in the retrograde direction, i.e., in the opposite direction to the planet's direction of rotation. For this reason, Triton may be a Kuiper Belt object captured by Neptune. It is also the only moon, along with Phobos, one of Mars' 2 moons, to approach the object around which it orbits. Our moon, on the other hand, is moving away from the Earth by about 3.8 centimeters, or 1.5 inches per year. While flying over Triton, Voyager 2 observed geysers 8 kilometers or 5 miles high over 180 kilometers or 60 miles, all concentrated in the region of Triton currently facing the Sun. These geysers would therefore have a solar origin. Researchers believe that Triton harbors fairly recent cryovolcanic activity, which explains the nature of the terrain observed by the Voyager 2 probe on its surface. Like Europa, Ganymede, Titan, and Enceladus, Triton could be home to an underground liquid ocean. To find out more, a mission project had been developed, the Trident mission, but it was not selected to be part of NASA's Discovery program. Instead, missions to Venus were chosen. No doubt another mission will be developed to answer the many questions scientists have about this mysterious moon. Where do its geysers come from? Why is its landscape constantly changing? Why does it have an intense ionosphere? Let's end our exploration of the mysterious moons of our solar system by getting a little closer to Earth. We're on our way to Mars and its 2 moons, Phobos and Deimos. These 2 moons share many characteristics with C-type asteroids, primitive bodies dating back to the genesis of the solar system. But contrary to what researchers have long believed, these are not primitive celestial bodies that were attracted to Mars from the asteroid belt like Triton. Not only is Mars' gravitational pull too weak, but their orbits are too circular. Phobos and Deimos are more likely to be the result of a collision between Mars and a giant celestial body. Perhaps these 2 moons were born at the same time, but their trajectories are different. Phobos is approaching Mars by around 2 meters every 100 years, while Deimos is moving away. In fact, Phobos is the closest satellite to its planet in the entire solar system. Its surface is dotted with craters, fissures, and other marks left by meteorite impacts. According to the researchers, Phobos will be destroyed in 30 to 50 million years due to deformations caused by Mars's tides and gravity, while Deimos will probably move away and emancipate itself from Mars' gravitational pull. In any case, these 2 moons are unlikely to harbor life. In the quest for extraterrestrial life, it's Mars that interests researchers. Europa, Ganymede, Callisto, Titan, Enceladus, Triton. All these moons could be inhabited by forms of life we can't yet imagine. Research carried out in recent years on the moons of our solar system has shown us that there are worlds not so far away from us that are very different from our own, and yet could be home to extraterrestrial life forms. But Is life on these seemingly cold and hostile moons possible? On Earth, we've discovered that life can cope with far more extreme conditions than previously imagined. Some microbes can live in arid deserts, in lakes saturated with arsenic, or on the walls of caves dripping with sulfuric acid. Environments that are toxic for us can be conducive to the development of other types of living beings, ultra-resistant organisms, unsuspected forms of life. Everywhere on Earth, life manages to thrive. So why not in underground oceans, sandwiched between several layers of ice and maintained in a liquid state by an internal energy source? Recent discoveries have prompted researchers to rethink their models and re-examine what they already know. Worlds that had previously been considered too hostile are now being re-examined and analyzed from a different angle. Whereas before, the search was for Earth-like planets, the field of possibilities has been broadened by looking at other types of celestial bodies, which offer other conditions and environments, and which may favor different types of chemical processes, with a result that could well be life.